Welcome. Today we're going to talk about extreme values, and what goes very nicely with it is the extreme value theorem. Then we're going to apply the extreme value theorem, or when it can't be used, we're going to just find the extreme values. What is an extreme value? An extreme value is, well, here's the theorem, but what an extreme value is the highest a function gets or the lowest. So last time we talked about local mins and maxes, or at least a little bit on graphs, but an extreme is the absolute min or max. It's the absolute highest. There may be several peaks. The top peak is the absolute max. The lowest valley is the absolute min. Now, how does this relate to the extreme value theorem? The extreme value theorem says if you've got a function that's at all nice, continuous, we're going to actually work with better than continuous. Suppose it's continuous on a closed, bounded interval. That's pretty important, and we'll talk about that in a second. If it's in a closed bounded interval from A to B or wherever, then f has an absolute min and it has an absolute max. That's all the theorem says, is they exist. It doesn't tell you how to find them or anything. But let's think about this for a second. If you start somewhere and you end somewhere and you're continuous, in between, you can wiggle, but you can't suddenly have an unbounded upper or an unbounded low. It's got to have a bound on top. It's the best it can get. In this case, look at this function. The top occurs at the endpoint. So the endpoints are actually going to be places we look at here. Other places we look at, so we're going to look at the endpoints. We also look at the critical points, because those are in the middle, the local mins and maxes, plus other points. So we look here, here, looks like there's a critical point. And now, the nice thing about the extreme value theorem is that we know one of them is the absolute min. We know one is the absolute max. So all we have to do is find these places, plug them back into the original function. The biggest one, well, that's the absolute max of the whole function. Why? Because one of these is the absolute max. Just plug it back in, figure out which is the biggest. Likewise for the absolute min. If that didn't make much sense, it's okay. Let's do an example and it'll make more sense. Try it. Find the absolute min or max, well, absolute min and absolute max of x squared e to the x on this interval. I'll give you a couple seconds to try it out. Okay, now, how do you do this? Well, what I said over here is we need to look at the endpoints and the critical points. So let's find the critical points. The critical points are where this has a zero derivative or a derivative that doesn't exist. Well, let's take the derivative. Hopefully, you know this is the product rule. So the product rule says the derivative of the first times the second plus the derivative of the second times the first. Now, e to the x behaves very nicely. So does 2x, so does x squared. This is all a very nice function. It's going to exist for all values of x. But it could be 0. So let's factor this. I can factor an e to the x out, and I can factor an x out, and I can factor a 2 plus x. So if I want that to be 0, then one of these three has to be 0. We've already discussed this in a different video, but e to the x can't be 0. It has no possible way to be a solution. That's not a problem. No solution from that one is not a problem. It just means that one isn't one of the answers. This one, x equals 0, well, that's done as a critical point. And x plus 2 equals 0, that means x equals minus 2 is a critical point. Now, this is kind of an odd choice because none of these critical points is inside of there. Now, what does that mean? Well, we don't really care about anything outside of this region. We only care about 0 to 3. If any of these were inside there, we'd care about that one as well as the endpoints. But our list of interesting spots includes the endpoints, and then any of the critical points we found that are in that region. 0, well, it's sort of in there, but it's already in our list. Minus 2 is not in that region, so we don't care. So, those are our interesting points. What does that mean? That means the absolute min and the absolute max are in this list. How do we find them? Well, plug them into the original function. Not into the derivative, plug them into the original function. If I plug 0 in there, I get 0 squared times, well, I'll get 0. If I plug 3 in, I get 3 squared, e to the 3. I don't actually even have to calculate this out. I'm going to. But I don't need to know what that is in a decimal. Why? Because, well, this is 0 and this is positive. But let me try that out. 9 e to the third. 180 point something. So this is going to be the absolute min of the function. This one's the absolute max. Why? Because we know the absolute min and the absolute max are on that list. And this one's the small and this one's the large. Okay, let's try another example. This one's not going to be able to use the extreme value theorem. Find the absolute min and max of this on this interval. Why does the extreme value theorem not apply? This is a closed interval, but it's not bounded. There are no endpoints for this interval. Well, you might say infinity is, but infinity is not a spot. It's a direction. Infinity goes that way, minus infinity goes that way, forever. There is no spot that is infinity or minus infinity, so we don't have endpoints. That's going to complicate things. But we're still going to want to look at critical points. So our first step is still looking at critical points. What's the derivative of this? Well, quotient rule. Derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. 0 times anything is 0. So this is minus 2x over 1 plus x squared, quantity squared. Now, critical points are where this is 0 or doesn't exist. So they're where the top is 0 or where the bottom is 0. Minus 2x equals 0 is pretty easy to solve. X is 0. Over here, something squared is 0. Well, if something squared is 0, you know when you've got a number, you square it, you get 0? That means the number is 0. So the something is 0. Solving that, we get x squared is minus 1. Hopefully by now you realize real numbers, that can't happen. There's no solutions here. So how many critical points do we have? Just one. How does that work? We need a max and a min. But remember, the extreme value theorem doesn't apply, so we don't actually know if a max or a min even occurs. An absolute max or an absolute min might not be on this graph. So why do we do this? How do we know if it's a max or a min? We're going to have to do something other than just plug values in. We're going to try looking at the derivative of the function. The derivative is 0 at this critical point. But for negative values, like a negative 1 here, what is this derivative? If I put a minus 1 in, well, the bottom is squared, so it's positive. The top, minus 2 times minus 1 is positive, so I've got a positive slope. Positive slope, what does a positive slope look like? It goes like this. The slope is going up here. Likewise, at positive 1, we've got a negative f prime, so we've got a negative slope. Everywhere before this, the function's going up. Everywhere afterwards, the function's going down. Because there's only one critical point, and the way these two sides work in terms of f prime, we know this is an absolute max. And we also know, since it keeps going down and it keeps going up, there is no absolute min. Now, that may be unsettling. It was nice with the extreme value theorem. When we had square brackets, a closed bounded interval, we always had an absolute max and an absolute min. Here, because we don't have that, we aren't guaranteed that. In this case, we have one of them, but not the other. We might have both, we might have none. In this case, we have one. Hopefully, though, this gives you an idea, and you can try it out yourself. Until next time, this is Dr. J.